Hi guys, welcome. This is going to be your final review video from me in preparation for the AP exam. I will, after this video I've got some copies to run. I'm still looking for a good chi-squares explanation on YouTube. When I find it, excuse me, I will upload it and I'll try to, if I get some time, I'll try to include the necessary calculator functions you would do for chi-square distributions also. This video, the whole goal is to present with you a recap of the sampling distributions that you've seen in this class regarding proportions and means, their conditions, whether or not you should choose a normal bell curve or a t-distribution, and also the reason I'm here on the AP Stats reference sheet. For each of these distributions, I want to make sure that you know where to look to find the appropriate standard deviation or standard error calculation for the distribution that you're building. Okay, I think hopefully you get a lot out of this video. What I will do with these notes is I will post them to my big campus completed, in addition to obviously the link on YouTube where you can watch all of this content. But recap this for yourself, study this. Students more this year than I have seen last year have struggled with understanding which distribution to use when, and I think a good reason for that is partly just because with the retesting that we did a couple of times this year for quizzes and tests that put us behind for chapters 23 and 24 covering those. So anyway, I feel like this is needed. All right, so we're going to start by looking at sampling distributions for proportions, and let me go ahead and draw for you. First distribution that we'll look at is a sampling distribution model for one proportion. Okay. Well, every bell curve that you use for proportions is going to use the normal bell curve. So we are going to have here, if we want to talk about where sample proportions lie, the expected value of a sample proportion on this bell curve is just P, which is the population proportion, and then your standard deviation of the sample proportions on this curve hinge upon rad PQ all over N, okay? With your conditions being the following three. Randomization, don't abbreviate that on the AP exam. Your 10% condition and success failure. Again, write out success failure on the AP exam. Okay, so where can you go if you know you need to use a sampling distribution model for one proportion? Where do you go on the stats reference sheet? Well, it is the second of these important standard deviations that's given to you on the second page of the AP Stats reference sheet. So it's the standard deviation of statistic for a sample proportion. It's P times 1 minus P. Realize that that's just Q all over N within the radical. Okay, so there's a sampling distribution model for one proportion. Well, let's talk about what a confidence interval for one proportion looks like as well. Okay, well, same thing. It's going to use the normal bell curve, not the t-distribution. It's centered on, we know confidence intervals use sample data to make estimates about population information. So the expected value of a sample proportion is just your sample proportion. That's your best guess, so to speak. And because you're using sample data, you use a standard error, not a standard deviation for p hat, which is square root of p hat q hat all over n. Okay? Conditions are the exact same. Even though you're working with sample data, you're still just checking randomization, you're checking the 10% condition, and you're checking success failure. Okay? So we've seen kind of a theme here. When you're talking about a single proportion so far, your conditions are randomization, 10% success failure. You're using the normal bell curve. There may be a difference as to whether or not you're working with standard error or standard deviation, but that depends upon whether or not you have population or sampled information to work from. Finally, we've got a hypothesis test for one proportion. Okay, again, uses the normal bell curve. And let's say your hypotheses are that the null is your population proportion is equal to P naught, whatever value that may be, and your alternative is that your population proportion is not equal to P naught. I don't really care what the alternative is here. I'm more interested in showing you how the null affects the bell curve. Well, the expected value of a sample proportion on this bell curve comes from your null hypothesis. Remember, that's your assumption of innocence, so to speak. If you think about this as the courtroom of law. Let's see. So P naught would be your assumption for where sample proportions are going to cluster around. That'll be your mean. And then here, because you're working with population information, we call this the standard deviation of P hat, which is, again, P naught, Q naught, all over N. Your null hypothesis proportion times Q naught divided by N. Your conditions are the same three we've been seeing. Randomization, 10%, and success, failure. Again, please don't abbreviate those on the AP exam. All right, so check it out. For the first three distributions, all talking about a single proportion, you have the exact same conditions. Randomization, 10%, success, failure, a second time, a third time. Normal bell curve, 3 times. Standard deviation calculated the same way. Sometimes we'll call it the standard error if you've got sample data. Okay, so now let's make the jump to, not means yet, let's continue to talk about proportions. Let's talk about the sampling distribution model. Sampling distribution model for 2 proportions. Okay, well, still working with the normal bell curve. The normal bell curve will be used anytime you're working with a proportion. That is centered on, if you want the expected value of P hat 1, your first sample proportion, minus your second, that is just P1 minus P2. Population proportion 1 minus population proportion 2. All right, well, to either side, if you've got population data to work with, you're talking about a standard deviation of P hat 1 minus P hat 2. This would be the square root of P1 Q1 all over N1 plus P2 Q2 all over N2. Okay, with the following conditions. You have randomization. You have 10%. You have success failure for each population. You've got 2 here to check. And then finally, your independent groups assumption, that is whether or not you think one population is going to directly affect the second. Okay, so notice the overlap here. Randomization, 10% success failure. Those stick around for all your tests, confidence intervals, and sampling distribution models for proportions. The only thing that's additional when you talk about a second population on top of the first is this independent groups assumption, which you'll have to check. And that's, again, just saying, does it seem reasonable to think that the first group is not affecting the success or failure of the second? Okay, so let's talk about a confidence interval for 2 proportions. Okay, so this again works with the normal bell curve. Normal bell curve. We've got at the center the expected value of a sample proportion from the first population minus a sample proportion from the second population is your P hat 1 minus P hat 2. It's your sample data. That's your best guess as to where the mean will lie. And then your standard error, because you're working with sample data, of P hat 1 minus P hat 2 is just the square root of P hat 1, Q hat 1 over N1 plus P hat 2, Q hat 2 all over N2, okay? With your conditions being the exact same as last slide. Conditions here are randomization. They are 10%. They are success failure for each of the 2 different populations and the independent groups assumption. All right, so there's a confidence interval for 2 proportions. Now finally, your hypothesis test. Hypothesis test for 2 proportions. We've We've got our normal bell curve that everything hinges upon. And let's say that your null hypothesis is that your population proportion from the first group minus the population proportion from the second group is 0, and that your alternative is that, I don't know, maybe that the first group has the second population, has a greater population proportion. So the expected value of a sample proportion from the first minus a sample proportion from the second should just be, from your null hypothesis, should be 0. And the standard deviation of a sample proportion from the first minus a sample proportion from the second group is the square root of P1 pooled, Q1 pooled over N1 plus P2 pooled, Q2 pooled over N2. Okay? Why do we pool? Well, the null hypothesis claims that there's no difference in the population proportions. So when you build the standard deviation, you need to pool together all the successes from your two different samples and find what that grouped sample proportion is, or population proportion is, so that you're not violating the null hypothesis. Conditions, same as in the last slide, are the following. Your randomization, your 10%, your success failure, and your independent groups assumption. Okay, so check it out. Let's recap real quick. Anytime you're talking about two proportions, you've got 4 conditions: randomization, 10% success failure, independent groups assumption. Those occur on your sampling distribution model, your confidence interval, and your hypothesis test. The standard deviation, if you're looking at your AP Stats reference sheet, the standard deviation for a difference of proportions is near the bottom on the second page. It's P1 Q1 over N1 plus P2 Q2 over N2. Now we're going to do that 100% of the time unless you're doing a hypothesis test for two proportions, in which case you pool the proportions so you don't violate the null hypothesis as you build your bell curve. If you don't pool, you might have a difference between your two different sample proportions. You might have a difference between the two different population proportions you believe from the data. And again, you'd be violating the null if you did that. So, confidence interval, two proportions, sampling distribution model, all set up same way. Bell curve used on all 6 of these guys. All right, so let's take the jump to means. Let's look first at the sampling distribution model for one mean. Okay, sampling distribution model for one mean. Well, whether or not we use the normal bell curve or the t-distribution hinges upon whether or not we know the population standard deviation that these sample means are coming from. So what we can say is that the expected value of a sample mean is the same as mu, whatever the mean of the individual people from the population is. For instance, let's say that X bar is looking at average heights of 20 students at a time here at Yorktown. And let's say we know that the true average across all heights, across all students rather, here at Yorktown is 5 feet 6 inches. Well, you would expect the sample mean to behave the same way. You'd expect that if you take 20 students' average amount, that you should see 5'6" on average, even just as you would see 5'6" across all students within the population. All right, so standard deviation for this, if you know the population standard deviation is sigma over the square root of n. Your conditions are a little different than they were for proportions. You continue to check the randomization condition, you continue to check the 10% condition, and instead of the success failure condition, for a sampling distribution model for one mean, you check the large enough sample condition. That is to say whether or not you feel like you've got enough people in your sample or things in your sample that you could use a bell curve to estimate sample means from that population. The large enough sample condition, you're looking at basically for smaller samples. Let's say you're taking a sample of size 10 of students from the population of students here at Yorktown. You need to make sure that you believe the heights of individual students here at Yorktown is both unimodal and symmetric. If you're taking a larger sample, let's say you've got 40 people, you need to make sure that the population of individual heights of students is unimodal but not necessarily symmetric. So the large enough sample condition is checked a lot like the nearly normal condition. Okay, moving on here, we've got a confidence interval for one mean, CI for one mean. Okay, and this is, because you're working with sample data for a confidence interval for a single mean, the expected value of x bar is just your sample mean, whatever that may be, and you're not talking about a normal bell curve. This is a t-distribution because you don't know the population standard deviation. So a standard error of a sample mean is going to be s over radical n. Okay? Remember that for one mean, your degrees of freedom are easy. That's just n minus 1, your sample size minus 1. Your conditions are the same as last slide. You have the randomization, no, I'm sorry, they're not, they're close. Randomization condition, 10% condition, and the nearly normal condition, where you're checking your sample data to see whether or not it's close to a bell curve. Okay, so if I say build a confidence interval for a single mean, I might give you 20 heights of students. The nearly normal condition is going to be checked by making a histogram of those 20 heights and seeing if that histogram is unimodal and symmetric. The distribution of my sample is unimodal and symmetric. Okay, so there's a confidence interval for one mean. Finally, for one mean, we've got the hypothesis test for one mean. Okay, this too is working with a t-distribution, where again, remember your degrees of freedom is just n minus 1, your sample size minus 1. The expected value of a sample mean depends upon what your null hypothesis assumption is. If you say that the mean, population mean is some h naught, the alternative, I don't really care what that is, that doesn't affect too much here, is less than that value or whatever, then your expectation for how a sample mean behaves should just be mu naught, whatever you claim the population mean was from the null hypothesis. Okay, your standard error of a sample mean is s over radical n, because you don't necessarily know anything about the population standard deviation if you're just making a claim about the population mean. Okay, that's why we use the t-distribution, because we don't know what the population standard deviation is. Your conditions are the same as last slide. They are randomization, there we go, 10%, and the nearly normal condition. Again, which you check by taking all your sample data, building a histogram, which you would display in your conditions, and then determining whether or not you think that's close to a normal bell curve. All right, let's go ahead and recap here. Notice for a single mean, you may use the normal bell curve, again, so long as you know what the population standard deviation is. Otherwise, you're going to use a t-distribution, and you're going to estimate your standard deviation with the standard error by using your sample standard deviation rather than the population standard deviation. Okay? Conditions change as to whether or not you use the normal bell curve, or dependent upon whether or not you use the normal bell curve or the t-distribution. If you're using the normal bell curve, you check randomization 10% large enough sample. If you're using the t-distribution, you check randomization 10% nearly normal condition. Notice there is overlap from sampling distributions of means and proportions, in that you're talking about the randomization and 10% condition regardless of means or proportions. Okay. All right. Finally, let's talk about the three curves that we have for a difference between two means. We have a sampling distribution model for two means. Okay? And you will probably be using the t-distribution here because it's unlikely that you know the population standard deviations for each of these two different populations you're talking about. All right, so the expected value of a sample from the first group minus a sample from the second group is just your population standard, or your population mean from the first minus the population mean from the second. Your standard error minus y2 is the square root of s1 squared over n1 plus s2 squared over n2. Okay, that's harder to remember for people. Let me show you where that's at on the AP Stats reference sheet. That is the first calculation this in the two sample category, two sample table. For a difference of sample means, it gives you this sigma 1 squared over n1 plus sigma 2 squared over n2. And I also forgot to mention that your sample mean standard deviation, if you're talking about a single mean, is listed in the single sample table as well. Okay, so they're giving you all of these standard deviation calculations. Those you don't need to remember for the AP exam. You need to know the conditions that you've got to check. All right. So conditions when you're talking about a sampling distribution model for two means are the following. You've got randomization, you've got 10%, you've got the nearly normal condition, and you have an independent groups assumption. Okay? That one we have seen before when we talked about two proportions. The independent groups assumption is basically checking again to see whether or not you think the first group of sample data is affecting the second group of sample data here. Okay, so 4 conditions to check for a sampling distribution model for two means. Okay, 2 curves to look at. We will have looked at 12 in all. Now we're going to look at the confidence interval for a difference between two means. Okay, so you're working with the t-distribution in all likelihood, and I need to show you guys how to find the degrees of freedom. You've seen it before, but it's rusty for a lot of you. The expected value of a mean from the first group minus a mean from the second group is just your sample means. Sample mean from the first minus the sample mean from the second. You're talking about a standard error of y bar 1 minus y bar 2 is the square root of, well, if you don't have population standard deviations, this would be S1 squared, your sample standard deviation from the first group squared, over N1 plus S2 squared, sample standard deviation from the second group squared, over N2 with the following conditions. Randomization, 10%. The nearly normal condition, which you're checking again from your sample data to see whether or not you have 2 good bell curves in the independent groups assumption. Okay, I feel like, did I write everything last slide? I did. Okay, all right, we're good there. So we've got 4 conditions to check here. Randomization 10%, nearly normal, again by taking your sample data, making 2 histograms and seeing if they're unimodal and symmetric, and then independent groups assumption is found by seeing whether or not you think the 2 different groups are affecting each other in any way. All right, so this you're going to use a t-distribution here. I need to show you on Wabbit as a refresher where to go to get your degrees of freedom. So let's see. I'm going to scroll down here to the W folder, Wabbit mu. You can use the same calculator function to find your degrees of freedom for a sampling distribution model for a difference between means, for a confidence interval for a difference between means, or hypothesis test for a difference between means. Same calculator function will work every time. The degrees of freedom calculation for a difference between two means is really clunky by hand, and you don't want to try to do it. It is also not just as simple as add up your two different sample sizes and divide by 1 or 2. So you can go down to a 2-sample t-test, click on that, use the stats that you can find, enter in your first sample mean, the standard deviation of your first sample. So I'll just enter in some random stuff here. 10 is my sample mean from the first group. 5 is my sample standard deviation. My sample size from the first group is 20. Sample mean from the second group, let's say it's 15. Let's say the standard deviation is a little bit bigger, 6. And the sample size from the second group is also 20. Okay. Don't worry about the null the alternative hypothesis thing here. You can leave that blank. Pooled, no. And we're going to calculate this. And there's the degrees of freedom. Something kind of seemingly random, 36.8. Okay. So again, from stat, test, two-sample t-test, you can enter your stats, the statistics, and calculate your degrees of freedom for this bell curve. Okay? All right, so there you go. Degrees of freedom you get from the 2-sample t-test function on your calculator. Now realize here, anytime you use a t-distribution, rather than finding a z-score, you call it a t-score, hence t-distribution. And anytime you would use a normal CDF from a normal bell curve, you're going to use t-CDF. Okay, so there's an easy analog from the normal bell curve to the t-distribution. Okay, so again here, that's t-CDF and a t-score versus anytime you'd see a normal bell curve. Let's see, let's go back to we had a sampling and distribution model for one mean. You would have been using norm CDF, and you would have used a z-score. Okay. All right, so last up, let's talk about the hypothesis test. For a difference between two means. Okay? Well, you probably won't know the population standard deviations, so you'll probably be using a t-distribution here with the expected value of a mean from the first group minus a mean from the second group, sample mean from each. Depending upon your null hypothesis, if you say the population mean of the first minus the population mean of the second groups is equal to 0, well, then your bell curve is going to be centered on 0. I don't really care what the alternative is, but I'll write out a sample alternative here. mu1 minus mu2 not equal to 0. Okay? So again, if you don't know the population standard deviations from each of these two groups, you're working with a standard error for y bar 1 minus y bar 2, which is the square root of S1 squared over N1, sample standard deviation from the first group squared, plus the sample standard deviation from the second group squared, all over your second sample size. And your conditions, again, same as last slide, are going to be randomization, 10% the nearly normal condition, and your independent group's assumption. Okay, so there you go. There is a comparison for you of the 12 different t distributions or normal z distributions, normal bell curve distributions that you would work with regarding